Hello students, today we're going to discuss a new topic named Deadlock, and after that I'm going to briefly talk about our midterm plan. So, um, so first let's look at what we have learned from last week. Last week we mainly learned CPU scheduling algorithm. So we learned four different CPU scheduling algorithms, which are first come first serve, shortest job first, priority scheduling, and round robin. We say that shortest job first is the theoretically best one, is the optimal one, but it's not practical because before we execute a process, we don't know how much time should we allocate it to that. So that's why people propose some uh, improvements over the first come first serve algorithm. So that's why we have the priority scheduling and round robin scheduling. So throughout the semester, CPU scheduling algorithm is one of the two most important topics. Okay, so it will play a big role in your midterm and also in your final exam. So be prepared for that. So let's look at the first topic that we're going to discuss today, deadlock. Deadlock. So here let's discuss deadlock. So if we're giving a computer, it only has limited resource. Let's say only one CPU, a certain amount of memory space, and certain amount of hard drive space. So so here, uh, a deadlock may happen if, say, all the processes that are ready to run cannot be allocated the resource that they demand for. So let's see where can the let me give you an example. Suppose here in the system in a computer system we have two hard drives, hard drive 1 and hard drive 2. Okay, we have two hard drives, and currently we have two processes that are running. So we have P1 and P2. So P1 already grabs the resource of the hard drive, the first hard drive 1, but it is asking for hard drive 2. Whereas so P2 so whereas at the current time the hard drive 2 is already grabbed by P2, but P2 is also asking for hard drive 1. So in this case, none of them is going to release the hard drive that they are currently holding, and then none of them can grab the hard drive, the additional hard drive that they ask for. So in this case, they're going to enter that deadlock, meaning that no process can really run. So, and this is really bad for operating systems. So here we can see that to tell if our system is going to experience a deadlock, so we need to construct a graph named resource allocation graph. This is a directed graph. I'm not sure if you have learned the topic of data structures and algorithms. If you have done so, you probably know what is a graph. A graph in computer science, a graph basically consists of multiple nodes and multiple edges. So that links these graphs. Okay, so this is a very simple graph. And so here when we construct the resource allocation graphs, there are going to be two types of nodes. The first type is consists of all the processes, whereas the second type consists of all the resources. So let's here usually we use circles to denote it. This node represents a process, whereas we're going to use rectangles to denote a resource. So here, for example, we have a type of resource which has four instances. For example, here we have four different memory cards. So then we're just going to create a big rectangle or square, and with four small squares inside it to denote that we have four instances of that. And more importantly, if a process is requesting an instance of a resource, we create an edge starting from the process to the resource. Whereas if a certain process is holding a resource, we're going to create a an edge starting from the resource to the process, meaning that this resource has already gone to that process. So here we can say this is one example of a graph of a resource allocation graph. Here we got three processes. We have three processes, and four different types of resources. We have one instance of resource one, two instance of resource two, one instance of resource three, and three instances of resource four. Here we can see that one instance of resource two has already gone to process one, and and whereas P1 is asking for R1. So here we can also say that the only instance of R1 has already gone to P2, where and also the other instance of R2 is already grabbed by hold by P2. So whereas P2 is asking for R3, and then R3 is currently held by P3. Okay, so this is what we can see, and here we need to after we construct this resource allocation graph, the answer that we want to provide is whether if these processes are going to be in a deadlock. So actually there are four conditions, four necessary conditions of a deadlock. First one is mutual exclusion, meaning that only one process can use an instance of a resource at a single time. Hold and wait, meaning that one process holds at least one resource. It only releases this resource after it finishes its execution. And then no preemption, meaning that a resource can only be released voluntarily by the process holding it after the process has already finished. And then circular wait. This is the most important one. It's like here we can say that we got a circle over here. So because by following the edges, we have a circle over here. Okay, so this is called circular wait. Meaning that there exists at least a circle in the resource allocation graph. And here we need to note that the directions of the edge counts. So if the direction of the edge is the other way, so here if the direction of the edge is not this way, it's not this way, it's this way, then there is no circle. So a circular wait does not exist in that case. Okay, if all of these four conditions hold, then there is a possibility of deadlock. Otherwise, there couldn't be any deadlock. So these four conditions are necessary but not sufficient for deadlock. So we need to remember that these are only necessary rather than but not sufficient condition. Okay, so so to let you know what is necessary but not sufficient condition, let me give you an example. Suppose let me say I can put it this way. I'm only going to buy a luxury car after if I can make, let's say, 100,000 per year. Okay, so so this is the statement. So which means that if I don't make 100,000 per year, I definitely will not buy a luxury car. But if even though I make 100,000 a year, it is not necessary for me to buy a car. So still I may choose not to buy a luxury car. So yes, this is what does necessary but not sufficient condition mean. Okay, so here is a resource. So here, if we go back to the previous graph, okay, so in this graph we can definitely say that all these four conditions are satisfied, and and especially this one, we got a circular weight over here. But however, this one is there is no deadlock over here because so we can let P3 first. We let P3 execute. So after P3 finishes its execution, P3 can release R3. So then we can let P2 grab R3 so that P2 already grabs all the resources that it needs. So then P2 can execute. After P2 finishes, so it's going to release R1 so that in this case R1 goes to P1. So P1 can also execute. So there is no deadlock. But however, if we slightly modify the graph in this way, so here you can see that even though these four conditions, even though these four conditions are satisfied, there is no deadlock. So, but if we just slightly revise the graph with this, with P2 is requesting with an additional edge, meaning that P3 is requesting R2. In this case, they're going to be in a deadlock, so no process can execute. So this is what I mean previously, okay? And also there is another way for us to tell if there is a deadlock or not. So this is called the banker's algorithm. So the intuition behind banker's algorithm is relatively easy. Say that when some people request a loan to a bank or mortgage to a bank, then the bank needs to say, okay, if the bank has sufficient deposit, sufficient funding at hand to approve this one, to approve this transaction. If yes, they will approve it. Otherwise, it's going to be a straight reject. So here the banker's algorithm really means that we need to check before we make a decision. So here let's say this is the next I'm going to introduce the procedure of the banker's algorithm. So suppose here we have the following resources. We have 4 tape drives, 2 graphic displays, 4 printers, and 3 disks. So we can create a total resource vector. So name the total. So we got 5, 2, 4, and 3, which means that each value just indicates the number of instances that we have for each kind of resource. And then next, let's say, consider that we have already allocated these resources among 4 processes as demonstrated. So here we got 4 processes that are running, got 4 processes that are ready to run. So we got process A, which takes 2 tape drives, 1 printer, and 1 disk drive. So and then process B grabs 1 graphic card. Process C grabs 1 tape drive, 1 printer, and 1 disk drive. Process D grabs 1 tape drive, 1 graphic card, and 1 disk drive. So remember that our total vector is 5, 2, 4, 3. And here we can get another vector called allocated. Allocated meaning that how many instances of each type of processes of each type of resource have we allocated. So here we can see that for tape drives we just need to sum up over this column. So we already allocated 4 instances of them. For graphic card we already allocate 2. For printers we already allocate 2. For disk drive we already allocated 3. So by taking the difference between them, we can get another vector named available, meaning that how the number of instances that are available to be allocated. So that are available for further allocation. So which is 1, 0, 2, 0. Okay, so this is the available vector. And next, let's look at the resource that each process is still asking for. So this means that in addition to these allocated resources, each of them is still asking for more in order to be able to execute. So process A is asking for process A is asking for 1, 1, 0, and 0, meaning that it is asking for one tape drive, one graphic card. Process B is asking for 0, 1, 1, 2. Whereas process C is asking for 3, 0, 1, 0, 0, okay? Process D is asking for 0, 0, 1, and 0. Remember that our available vector is here, okay? It is 1, 0, 2, 0. It's 1, 0, 2, 0. So here we can say that the number of resources that are available is so with this resource available resources, we are able to satisfy the need from process D so that we can let D run first. We just let D run. So then we allocate this the additional printer to process D, and so that we let process D run, and after process D finishes running, it's going to give back, it's going to release the resources that it takes. So then the number of available resource that we have is going to be this available number plus this available plus this vector. So it will be 2, 1, 2, 1. So after that, the available is going to be make this a little bit smaller. So it's going to be 2, 1, 2, 1. Okay. So and after that, okay. So after that, we got this number of ready processes, so we can erase process D because it's already finished execution. With 2, 1, 2, 1, let's look at which process are we going to able to satisfy. Here we can say that 2, 1, 2, 1, any value in 2, 1, 2, 1 is larger than or equal to 1, 1, 0, 0 and 0, 1, 1, 2. So here we are able to satisfy the need from either process A or process B. So for example, if we choose process A, which from these two processes, let's say we choose to run process A first. Actually, we can also run process B first. So then we satisfy the need from process A and let process A run. After that, process A is going to release the resource that it occupies. So that we got 4, 1, 3, and 2 in the allocation vector after A finishes execution. And so with 413A, we are able to satisfy either B or 32. We're able to satisfy either B or C. So let's say we satisfy B first, and then we give the resource that B is asking for, and after B finishes execution, it is going to release the graphic card. So then we got 4, 2, 3, 2, and after that we can let process C run. So then the available process is going to be 5, 2, 4, 3. So which is the total vector. Okay, so in this way we can see that there is a sequence which can guarantee that there is no deadlock. So we call this one, we call DABC a safe sequence. It's a safe sequence because there is no deadlock, and then we see the current state of the computer is in safe state. Okay, the current system is in safe state because there is no deadlock. Okay, so this is how can you know if there is a deadlock or not. So in order for you to better prepare the midterm for the deadlock part, pay attention to these 4 conditions as well as the banker's algorithm. Okay, so go through the procedure that I went through over here. Okay, so this is the deadlock algorithm. Next, I'm going to talk about the midterm. So the midterm is going to be in the first week of November. So ideally, I want to allocate it to Monday, sometime on Monday afternoon or evening. But still, I need to check your availability. So I'm going to send out an email or doodle an announcement on Canvas to ask for your available slots. So if most of the students agree on some date, agree on a certain time, and if only a couple of students cannot cannot have take the exam during that time, I will give them a special accommodation. Okay, so here the the midterm is going to be 75 minutes long. Okay, so it's not going to be too long, and it's going to cover our materials from lecture 1 to lecture 8, which includes kernel, our operating system kernel, system call, process, thread, interprocess communication, CPU scheduling algorithm, and deadlock. So and it's going to worth 20% of your overall performance, and there are going to be 4 different parts of the in the midterm. So the first part is true or false, so pretty simple. The second part is short answer, so which ask you, okay, so to explain very simple concepts, so you only need to answer this question with at most 2 or 3 sentences. So like the questions in this part include some concepts and some Linux comment, and then following that is the detailed explanation. So detailed explanation in this part, I'm going to give you 2 questions. One regarding CPU scheduling algorithm, which is pretty much like your homework 1, and the other one is like the deadlock. It's like the banker's algorithm that we just went through. And then so the last part is going to be program review. So the format is that I'm going to provide you a small program and ask you, okay, what is the expected output. So here I don't expect you to write down any code by yourself, but I want you to show me that to demonstrate that you understand what does the algorithm do. So the topic here could be either process or thread creation, or could be process synchronization. So if you are not sure about what I'm talking about, go back to check the slides in those lectures. And so to help you better prepare the midterm, I don't want you to take 10 hours to prepare it. Instead, I just want you to spend 2 or 3 hours on it. So I provide the following slides, which covers the most important points. Okay, so if you just go through this slide, the following slides, you'll be able to get at least 80 out of 100 from the midterm. Except you actually, I'm pretty safe to say you can pretty much get everything correct, except for maybe the only exception is this part, is the program overview part. If you want to do good at this part, go back to check the slides of the process and thread creation and synchronization part for what kind of code I have showed in those lectures. Okay, so I assure you that the midterm is not going to be too difficult. No, not at all. So it's going to be relatively easy, and because as you can see here, you are only giving 75 minutes, and with 2 or 3 hours preparation, I think most of you are going to be do sufficiently good. And also because of this pandemic, we're going to do the midterm remotely. So what I ask you to do is that okay, after in the beginning of the midterm, I'm going to send to release the midterm exam paper on Canvas, so that you can check it, and then you just need to print it out, or say or you don't, if you don't have a printer with you, you don't need to print it. You just work on the answers. So either you just create a Word file which describes the answers for each question, or you can just write down your answers on a piece of paper and but you need to write it down in a clear way, okay, in a clear format, and take a picture of it and upload it to Canvas by the end of the midterm, okay, which means that in 75 minutes. And so yes, that's our lecture for today, and have a nice week.